السلام عليكم يا شباب، ايه الاخبار؟ ان شاء الله النهارده معانا باشمهندس محمد مسمودي. هنشرح واحد من اهم الالجوريزمز اللي ممكن اي حد نون تكنيكال في الكوانتم يكون سمع عنها. شور الجوريزم طبعا مشهور جدا عشان موضوع اللي هو يعمل ديكريبشن للار اس اي، وبيكون اكبر ثريت في الكرنت انكريبشن يعني في الريل وورلد عندنا. مش اتفضل بقى يا باشمهندس.
متشكر يا عبد الرحمن. مرحبا بكم كلكم. النهارده هنعمل وركشوب على الشور الجوريثم. هعمل شير السكرين بتاعي. اوكي. بتسمعوني كويس؟
الصوت واضح والسكرين باين، الله ينور.
بيرفكت. اوكي. فعني النهارده هنعمل اوفر فيو على شور فاكتورينج الجوريثم. في السيشنز اللي فاتت اكتشفنا مع بعض الكوانتم فورير ترانسفورم، كوانتم فيس استيميشن. اكتشفنا مع بعض algorithms اللي عندهم direct impact في ال real world applications. والنهارده هنشوف algorithm اللي حيغير حرفيا حيغير الابروتش واللاندسكيب بتاع الكلاسيكال cryptography and classical security in general. Okay, let's begin with the RSA encryption. That stands for Rivest, Shamir, and Adelman. It's a classical encryption protocol that we will be diving deep, and you need to understand first to understand afterwards how quantum can surpass and can break such classical encryption schemes. Okay, let's start with a quick example. Let's suppose that a person, Alice, wants to send some information to another person, Bob, and she wants to encrypt it so that eardroppers cannot know and cannot retrieve that information that's being sent to Bob. Alice will have a public key, NE, that we will be using to encrypt her data. Then she will send the information to Bob, and with the help of a private key, Bob will use the private key to decrypt the data. Only Alice and Bob can know the private key, but everyone else knows the public key that is public to everyone. So, in general, Alice will use her public key to encrypt the information and send it to Bob, and with the information or with the keys contained in Bob, he can decrypt the data and can retrieve the data without anyone else retrieving the data with him. So there's a question right here. Alice will, she will encrypt her data with the help of a public key. And the public key is public knowledge. Everyone else has access to Alice's public key. So thus, with the public key, why can't anyone else know with what is the message that was sent by Alice to Bob? Why can't anyone else decrypt the message sent by Alice to Bob? And the answer is a simple mathematical fact, is that large numbers are really hard to factorize. If you have a certain large number, and for example, noted n, it's really, really hard and really computationally expensive to factorize it into two primes. So if you want to find p and q, which are two prime numbers that give us n equal p times q, it's really, really hard to do this factorization. So with the help of this fact, Alice can encrypt her data and send it to Bob. And if anyone else in here, in the process of this message sending, wants to decrypt data, wants to eavesdrop on the message sent to Bob, he needs to decrypt, or he needs to, factorize the number n, which is a big number, into two prime numbers. And this is mathematically and computationally expensive in the classical case. we will be seeing afterwards in the quantum case if it still is valuable or not. Okay, before we move on into the rigorous algorithmic description of the RSA algorithm, let's do some modular arithmetics. If you have a certain number, an integer a, which is in the integer space z, and n, which is another integer in the integer space z also, a is equivalent to b mod n. That is, a is equal to n times k plus b. If this writing right here is equivalent to saying that in here, this is equivalent to saying that a is equal to n times a certain other integer k plus b. So this is a very important way to describe numbers in relations with each other. For example, if we have 7, a is 7 and n is 3, we know that 7 is 2 times 3 plus 1. So 7 is equivalent to 1 modular 3 or mod 3. So it may you may understand it as 7 can be described by full, if you will, full combinations or full numbers of 3 plus 1. So 1 here is, you can see it as the remaining from the division of 7 by 3, or you can see it as the extra number from all the 3 combinations or 3 multiplications in 7 itself. If we have, if you will, a is a multiple of n, then b is automatically 0. So if we have a is equal to 8 and n is equal to 4, 8 is equivalent to 0 mod 4. That is, 8 is a multiple of 4 because the residue or the leftover from the division of 8 by 4 is 0. So b here, if you notice, is always in the interval 0, 1, 2, etc., up until n minus 1. So 8, for example, is equivalent to 3, is equal to 5 times 5 is equivalent to 5 mod 6 because 6 times 0 plus 5. Then a, then b will end up being a overall arithmetics, and we are going to use these notations excessively in the next notions. And let us now introduce the RSA key generation. How can we generate keys in the RSA encryption scheme? How can we generate keys that are resistant and that cannot be penetrated or that cannot be decrypted by a third party from the mathematical property that we introduced earlier, is that large numbers are really hard to factorize. Okay, in the RSA key generation, there is a certain, you can see it as an algorithm or a protocol to generate these keys. And here we will be picking up 2 large prime numbers, P and Q. So P and Q are our first numbers or first integers in here. We are going to pick them as large prime, prime numbers, and n, our large number or our key that we are going to generate and we are going to use to ensure safe communication, will be P times Q. Then we are going to compute another number, which is lambda of n. Lambda of n being in here the least common multiple between p minus 1 and q minus 1. P and q are prime numbers. So if we want to get meaningful results from the least common multiple, we are going to use p minus 1, q minus 1. And this is called the Carmichael-Quotient function, lambda of n. This is the second step in the RSA key generation. Afterwards, in the third step, we're going to choose an encryption exponent, E, a random encryption exponent E, where E is more than one, bigger than one, and less than lambda of n, the Carmichael-Quotient function. This is the third step, and we are going to compute D is equivalent to E minus 1 to the power of minus 1, or the inverse of E mod lambda of n. This notation is equivalent to saying that D times E is equivalent to 1 mod lambda of n. So this is the modular. D is the modular inverse of E mod lambda n. And we can see that D times E is equivalent to 1 modular lambda of n, because if you multiply by E from the left side and the right side, we end up with 1 on the right side, and the left side we end up with D times E. Now we have our keys, the public and private keys, the N and D. So now we generated our keys. How can we use them to ensure safe communication? The public key is the combination NE, and the private key is the combination ND. Now we generated, as you said, the two keys, the public key NE with the selection of the encryption exponent E, and we generated the private key with this generation of the D, which is the modular inverse of E. Now we are going to use them to encrypt and decrypt data. Let's suppose that our data is a certain number D. You might say that our data can be a string, if you will, sequence, some letters, something like that. Every single type of data can be translated or can be transferred from its row, if you will, row initial state to a certain number. And we are going to call it right here, big D. So we are going to generate the encrypted data. We have our initial data, D. We are going to generate the encrypted data, E. We are going to define it as equivalent to D to the power of E mod N. We are going to use our data, use the public key to create the encrypted data. And if you want to create also the decrypted data, we will take our encrypted data, the if you will, the recipient or the receiver of information, or the receiver of the encrypted data will decrypt it, E times D. He will use the private key and do the decryption of the data by raising E to the power of D. So it will be D times E times D. Here we just replaced the E, which is with its equivalent form. So it will be D times E, and all of it will be times D. And then we will be receiving it being equivalent to D mod N. And this actually works because of a certain theorem. If A is equivalent to B mod lambda of N, and C is co-prime to N, that is, they share no factors, the greatest common denominator or divisor. I forgot the English name, but it's GCD. It's greatest or its biggest common divider. Yes, that's it. Between C and N in here, C and N is equal to 1. That is what C is co-prime to N means. So if these two eventualities, or if these two properties are present, we have C times A is equivalent to C times D mod N. And in here, we have D times E is equivalent to 1 modular lambda of N. Because in here, this is the direct result of the modular inverse property. Thus, we apply this rule, we get that D times E multiplied by little d mod N will be equivalent to D to the power of 1 modular N, of course. So this equivalence is this equivalence is verified. So in here, in the encrypted data, we successfully took our initial data D, transferred it to another form of data E, with the help of the public key, of course, and in the decrypted data and in the step of decryption afterwards, we used the private key that allowed us to transfer from the encrypted data in here to the decrypted data or the original data in general. So in here, we ensure that our data, with the help of the key generation, if you will, steps and the key usage steps, we ensure that our data, original data D, that was sent by Alice and encrypted by the public key of Alice, that was encrypted by the public key of Alice in a way that only the fuel recipient or only the destination will know or will be able to decrypt it with the help of the private key. We ensured safe, if you will, communication. But here, a certain problem arises. If we know the P and Q, if you have a certain eavesdropper in here, as we said earlier, and he knows and he has access to P and Q, the large prime numbers that we talked about, that were generated or that were picked in the RSA key generation step. If you have a certain eavesdropper in here and he had access to P and Q, then he can, if you will, he can do the entire key generation steps. I can do the first step, the second step, the third step, and the fourth step, and get the private key of the recipient or the destination. And if he has the private key, he can reach the decrypted data. So in here, if our eavesdropper in this particular step can have access to P and Q, that is, he can factor the number n, the large number n, to P and Q, he can decrypt the data and he can deduce the information that was sent by Alice to Bob. But fortunately, RSA will work, and this will never happen because as we said before, the factorization of n to two large prime numbers, P and Q, is extremely difficult and is extremely computationally expensive. And this is the principle of why RSA protocol and many other encryption protocols work, is that they use this mathematical notion and complexity notion, is that it is impossible for our eavesdropper to conclude or to retrieve the P and Q numbers, and that is, it is impossible for him to get the two large prime numbers to extract the private key and decrypt the data. And this is the principle why these classical algorithms worked up until now. That's where Shor's algorithm comes in. So before we move on to the coding notebook, does anyone have a question? Okay, let's move on to the coding notebook. In here, in our in this session's notebook, I just included some installations if you don't have Qiskit and some other libraries installed, and some imports from the Qiskit libraries and some other libraries. I included some helper functions to allow us to do the modular exponentiation, constructing some mappings afterwards in the quantum part of our fuel workshop. And the quasi-modular exponentiation, we are going to see this in a bit, and the fraction plotting function that helps us in the plotting step of our workshop. Okay, let's now dive deep into the RSA key encryption. Yes, does anyone have a question? Yeah, of course, of course. The notebooks and the slides of our workshop will be sent afterwards in the GitHub link. But the important thing is that you guys are understanding and you guys are following me in the steps of the notebook, because it might get confusing with the number of the variables and the integers and something like that. But the important thing is that you guys are following me, that you guys are following me in here. Okay. Okay, now we are going to try and actually code these steps of the RSA key generation and apply our algorithm to effectively achieve secure and safe transmission of information. Let's do our first step, as we talked about earlier. We are going to pick two large prime numbers, P and Q, the first step in the generation of the RSA keys. We are going to pick the large prime numbers, P and Q, to construct afterwards the big N number. So we can pick 1999 and 4457. I included a link in Wikipedia to find other numbers if you guys want to experiment with more numbers and more trials in the RSA key encryption scheme. We can generate the number n, and then we are going to generate in the second step, we're going to compute the lambda of n, the Carmichael totient function, which is the least common multiple between p minus 1 and q minus 1. So n, as you guys see in here, is a very big number, and lambda of n, the totient function, will be equal to this particular number, which is also another big number. Now, let us try to find an E with if you will, with conditions that comply to our initial conditions or our initial requirements. And if we iteratively and we repeat the trials in range 100 in here in our code until we find the exponent, this encryption exponent E that has a greatest common denominator between him and lambda of n, that is equal to 1, so that it complies with our rules or with our conditions that we stated earlier. And after this particular for code in here, we can extract our resulting E, the exponent in here. We can compute also the modular inverse of our resulting E with the function mod inverse that we defined earlier, and we can get this particular number. So in here, we did the first step. We generated the Carmichael totient function. We generated the encryption exponent, satisfying the conditions that we stated earlier, and we are going to compute the modular inverse of E. At this particular step, we have all the public key and private key requirements, and we have our keys that are ready for our RSA encryption and for our RSA safe transmission of information. Let's pick a certain message, which is in here, hi. We want to use a message that is originally a integer number. We are going to use a general string in here, or general word, which is hi. And we are going to turn it into an integer using the ASCII keys, which is an implemented, if you will, way of transferring letters or chains of words into numbers in general. And we are going to use it, but there are other schemes that, and there are other ways that transfer information into purely integers, but we are going to use in here the most simple way possible, which is the ASCII keys, and we are going to transform it into a certain number, which is this particular number. We do our encoding of our message with the modular exponentiation function, and we do our decoding of information. In here, we just encoded the message, and in the real world case, we send our information from this step to our recipient or to our receiver, and the receiver will do the decoding of our message with the help of the generated private key that we talked about earlier. So this is an example of the execution of the RSA encryption scheme in here, and we achieved the desired feat, which is the safe and secure transfer of information from one person to another under a certain protocol that will enable just that person to decode the information. And if any eavesdropper comes in between of this information transfer, he won't be able to decode the information on his own, because he will need the numbers P and Q to complete the second, third, and fourth steps of the RSA key generations. And if he doesn't have the P and Q, he can't generate the number N, etc., etc. And this fact comes from that N. If he wants to deduce P and Q from N, because N is public knowledge, he cannot, because the factorization, as we talked about before, is really, really computationally expensive. This is up until this point, this is classically safe, but the quantum way of extracting these information, these vital information, there will be some drastic change. So before we move on to the quantum part, there is just a problem in here. You can try and play around with other values of P and Q in the Wikipedia link. And you can try also to do this particular RSA encoding protocol with a message with a value which is larger than big N, and see if this encryption still work or not. So up until this point, we finished the RSA understanding of RSA functioning and why especially classical encryption ways function, because the factorization problem is very hard to do classically, but in the quantum case, things will change. That's yes. There's another question. Okay, I'm sorry. I thought I heard some sound. If anyone has a question, please feel free to even interrupt me while I'm explaining the slides, because it's better to tackle problems and questions while I'm explaining. So that's where the Shor's algorithm comes in. For the Shor's algorithm problem, our goal is, if we have a non-prime number, big N, we want to factor it into the product of two numbers. So the classical bottleneck, or the classical problem that we encountered beforehand, we want to solve it, but with quantum tools and with quantum algorithms paths, or quantum algorithms ways. We can receive also A and B, the factorization results, non-prime numbers, because we can do the Shor's algorithm iteratively until we reach prime numbers. So if N gives us the product of two non-prime numbers, we can take each and every number and do the Shor's algorithm once again until we reach the final factorization. Okay, now Shor's algorithm comes in this particular bottleneck and tries to solve it. And we are going to see the approach of the Shor's algorithm. In Shor's algorithm, the first step is to choose a particular integer, a, called a, which is in the interval between 2 and n minus 1. N minus 1 is the same n that we introduced earlier with the public and private keys. And a must be co-prime with n. This is the first step. And before we move on to the second step, there is actually a certain theorem, a certain very important theorem in arithmetics in general. If a and n, two numbers or two integers, are co-prime, there will exist a certain number, natural number, m, such that a to the power of m will be equivalent to 1 mod n. So if we have a and n co-prime with each other, that is the greatest common, the GCD, as we said before, is equal to 1, there will exist a certain m such that a to the power of m is equivalent to 1 mod n. And we are going to consider r to be the smallest possible m. So we can have 1m, 2m's, a lot of m's, but the smallest possible m will be called r. And this number is very, very important in our session. You need to memorize it and to understand its functionality. Okay, from this theorem, we extract our number r and we input it in this particular step. We know that a to the power of r is equivalent to 1 mod n from its particular definition, from its original definition. Thus, a to the power of, we take this particular one in here and we move it to the left side of this equivalence. So we can deduce that a to the times of r minus 1 is equivalent to 0 mod n, evidently. But this particular expression, we can factorize it and it will become a to the power of r over 2 minus 1 multiplied by a to the power of r over 2 plus 1, which is equivalent to 0 mod n. Two cases arise in here. If r is odd, thus it will not be divisible by 2. So these two numbers in here will not be necessarily integers, because in here, this particular part will be an anomaly to reaching the fact that these two numbers are integers. R is odd in here, thus it is not divisible by 2, and thus these total two numbers are not necessarily integers. They can be not integers. In this case, we retry. We go back to our first step and we choose a different a which is included from 2, 3, 4, etc., until we reach n minus 1, which was another prime, another number a co-prime with n. And if r is even, we repeat this particular process until we reach r being an even number. If r is even in here, that is, these two numbers are integers, we continue to the third step. The third step in here is detailed in here. The product of these two numbers that we talked about earlier is equivalent to 0 mod n. Thus, n divides this product, because as we talked about before, the introduction to the modular arithmetics, if we have a in general, a number a, which is a multiple of n inside the modular part, thus the equivalence will become 0. B in here will be equal to 0 because the residue of dividing a by n is 0. So it's the same in here. This particular number or this particular product is equivalent to 0 mod n. Thus, n in here will divide this particular product. But n cannot divide this particular first term, a to the power of r minus over 2 minus 1, because if n divides this particular number, then by definition, as we talked about right now, a to the power of r over 2 minus 1 will be equivalent to 0 mod n. The residue of division of this particular number by n will be equal to 0. We take the minus 1 in here, and then a to the power of r over 2 is equivalent to 1 mod n. And this supposition is entirely incorrect, because by definition of the number r is the smallest possible number m, or the smallest possible integer m, that verifies a to the power of n is equivalent to 1 mod n. So in here, if this supposition is correct, we will be having another number, a to the power of r over 2, equivalent to 1 mod n. And this particular number is smaller than r. And r, by definition, is the smallest possible number that ensures this particular property. Then r won't be our smallest m. And this is absurd. Thus, n can never divide this particular part of the product. Now, two cases arise in here. So if n doesn't divide this particular number, there are two cases present. if n divides this other member of the multiplication in here, or of the product in here, thus we won't learn anything about the factors of n, as we are going to see afterwards, and we retry. We come to the first step as usual, and we pick another number a. And if n doesn't divide this particular second part of the product, then they share a common factor. Let's understand what is this. What does this particular condition mean? It means that n divides, sorry, the product a to the power of r over 2 minus 1 multiplied by a to the power of r over 2 plus 1. It divides the entire product, but it doesn't divide each part of the product in its alone. So it doesn't divide this particular part of the product, and this it doesn't divide this particular part of this product. Thus, the the factors of n will be contained in this particular number and in this particular number. Thus, they share a common factor. N and this number share a common factor, and n and this number also share another common factor. And if you want, and as we saw, as we talked about before, n will have two possible prime factors. Thus, one factor of n will be contained in this particular number, and another factor of n will be contained in this particular number. So if you want to extract the first prime number that constitutes n, we can define it as f1, the greatest common denominator divisor, sorry, between n and a to the power of r over 2 plus 1. F1 will contain, if you will, the first factor of n in here, and F2. Sorry, one moment. I'm extremely sorry for the disturbance. Okay, and F1, as we said, as we talked about right now, will be the first prime factor of big N, and F2 will be the second prime factor of N. So if we want to conclude what this particular process wants, it wants to, if you will, divide the number a over a to the power of r minus 1 to two numbers or two integers multiplied to each other. And these two integers and their factors will contain the first prime number p and the second prime number q. And if we want to extract these two numbers, we want to ensure, of course, two conditions: that r is even, so that we ensure that these two numbers are integers, evidently. And we want to ensure also that n doesn't divide this particular number, because if n divides this particular number, then p and q will be contained in this second member of the product. Thus, we won't know anything. We can't know anything about p and q because they are contained in one part of the product, and thus we can't extract it with the greatest common divisor method or with the greatest common divisor tool. But if p and q were, if you will, partitioned or were if you will, separated in the first member of the product and the second member of the product, thus if we will apply the greatest common divisor between n and the first member and n and the second number, we extract f1 and f2, which are e and q. So by this, if you will, method, we extracted the two members, or we extracted the two factors of n, and this is the dangerous, if you will, realization. With this particular algorithm, or with this particular Shor's process or the Shor's approach, we were successful in extracting p and q. And if we extract p and q, we can, if we will, deduce the lambda n number, and we can deduce afterwards the private and public keys. So Shor's algorithm in here was successful in doing and in cracking the bottleneck or cracking the barrier that protects classical encryption and classical safe communication in general. And the hard part in this particular program, this particular approach will be, if you will, exponentially more efficient than classical approaches. But the hard part in this approach is finding R, finding the number R, which is the minimum of the numbers M, natural numbers, evidently M, such that a to the power of m is equivalent to 1 mod n. So the, if you will, the Shor's trick in here, or the quantum trick in here, is the speed up in finding R, the smallest possible number m. So Shor's process in here wants to focalize, if you will, on this particular part. If we are given a certain number n, we want to pick a number a, as we talked about before, and compute R. And if we compute R, we can, if you will, move on to the next steps with the, if you will, the with checking if R is odd or not, and checking if n divides this number or not, and deducing afterwards f1 and f2, which are p and q, the prime factors of n. So Shor's, if you will, algorithm, or Shor's, if you will, process will focalize on this particular detail, and we will be diving deep into how Shor's algorithm achieves this particular feat. And if we, from a certain number n and a certain number a, can compute R, and if you will receive the number R, we say that we concluded quantum order finding. So Shor's process is if you will, at the heart of the entire protocol of finding P and Q. Shor's process receives a certain number n and a certain number a in the interval between 2 and then minus 1, evidently. And Shor's algorithm will try and compute R. So Shor's process will have an input n and a, and will compute R for the rest of the process to unravel. And this is called quantum order finding. I'm going to see afterwards why it is called quantum order finding, why the name quantum order finding. Okay, before we move on to the next part, does anyone have a question about this general process? Okay, perfect. We can move on to the next part, the order finding algorithm. So, as we talked about before, our problem, or our, if you will, issue at hand, is finding the minimum or the smallest possible number m, such that a to the power of m is equivalent to 1 mod n. From this sentence, we conclude that we have a lot of numbers that satisfy this, if you will, this property, but we want to achieve and we want to reach the smallest possible number m, which we will be calling R. So, for example, let's take, if you will, our numbers. Let's take this particular example. We are going to list a lot of numbers, which we will be calling b, and we will be calculating 7 to the power of b mod 15. In here, a will be equal to 7, and b will be and n will be equal to 15. So in this particular example, our inputs in our approach to crack this particular problem of factoring, we have as input a, which is equal to 7, and n, which is equal to 15, and we want to find R being the smallest possible number m, which is a natural number. Let's, if you will, list some possible numbers some possible numbers in our function in here. If b is equal to 0, 7 to the power of 0 mod 15 will be equal, 7 to the power of 0 mod 15 will be equal to 1 in here. If b is equal to 1. 7 to the power of 1 is equal to 7. 7 mod 15 is evidently 7 because 7 is less than 15. If b is equal to 2, 7 to the power of 2 is 7 to the power of 2 is 49, sorry. And if we do the consecutive divisions, we reach to the outcome of 4 mod 15. And so on and so forth. If we do this a lot of times, from 0 to 8, 9, 10, 11, etc., etc., we notice a certain periodic pattern. So 7 to the power of b mod 15 will be equal to 1, 7, 4, 13. 1, 7, 4, 13. 1, 7, 7, 4, 13. So our particular function that we want to find the minimum of number b, such that 7 to the power of b mod 15 has a certain pattern to it. 1, 7, 4, 13. 1, 7, 4, 13. And from this particular table, we can conclude that for b equal to 0, we have the outcome, which is evident. We want our number m, as we talked about before, to be not 0 because the outcome is 1 when m is 0. That is trivial. So we want to see what is the first number that achieves this particular condition apart from the 0. And we notice that if we plug in the place of m 4, we get 1, which is the first occurrence. So we deduce that r is equal to 4. We saw in here that m, as we talked about before, is the smallest number, smallest possible number m. We are looking for the smallest possible number m, such that a to the power of m is equivalent to 1 mod n. And if we plug in 7 to the power of 4, it will be equivalent to 1 mod 15 in this particular case, which is the first occurrence or the first number m that verifies the above condition. And our pattern repeats. The same condition will be verified by 8, which is 2 times r. It will be verified by 12, which is 3 times r, and so on and so forth. Thus, we conclude that our problem, our initial problem of Shor's algorithm, is that if he is given the number big N and the number A, he wants to compute the number R. And if we try a lot of numbers, a lot of M numbers, we will be finding that the power of M is equivalent to 1 mod N will be, if you will, a periodic pattern. And the first number of this periodic pattern will be R. In this case, R will be equal to 4. So here we found R from pure, if you will, table calculations. But this is an easy, if you will, example. If you have another advanced example, these calculations will not be very easy. And in here, we found our number R, and we follow it up with the rest of the steps, if R is odd or not, and if N divides this particular number or not, and we will be seeing if we retry and find another number A. But in here, we successfully found a number R, and we successfully, which is more important, deduced that in this particular, if you will, calculations, we notice a certain periodic pattern. And what is the tool that deals or that treats periodicity? Any periodicity in the entire, if you will, scientific calculations in general, it is the Fourier transform. The Fourier transform, in its, if you will, general basic definition, it is a tool, or it is a mathematical tool that deals with the periodicity of functions. It extracts periodicities and it treats it in depth. And in this case, we want to do these calculations on a large scale, on the scale of large numbers, which classical computations and classical algorithms can, up until this point, cannot deal with in an efficient way. So we want to resort to quantum methods. And if you want to resort to quantum methods, we are going to use quantum Fourier transform. In here, from what the name entails, our first problem was a problem of factorization. But as we, if you will detail and as we analyze our problem, our factorization problem became a order finding problem, a period finding problem. There is a period in here. If we find the period r in here, which is the first, if you will, value or the first number that gives us the condition mentioned above, if you find the period that gives us this particular condition verified, then we can proceed with our algorithm. Thus, the problem that was initially, as you said before, the factorization problem evolved into a period finding on an order finding problem. And as we talked about before, the QFT and especially the quantum phase estimation protocols and the quantum phase estimation algorithms that we studied in previous sessions, these are the tools, the quantum tools that deal with periodicity and periodic patterns in general. Okay, so let's recap before we dive in the amazing quantum stuff. Our process, our Shor's general Shor's process, gets a certain number n, big N, and he wants to factorize it into the product of two numbers, A and B. A and B in general. A and B in here, we want to factorize it in the product of two prime numbers because n will be the product of two prime numbers that we want. Thus, we want to extract the two prime numbers P and Q to, if you want to hack the communication between Alice and Bob and to disrupt this particular safe communication. We start by choosing a random number A from 2 to the number n minus 1, which is co-prime with n. A and n are co-prime. And with this particular theorem, we extract the number r that corresponds to A and n, the combination between n and A, the actual, the chosen combination of NA, and with this number R, if you will, we continue with calculations. We do this calculation, and we, if you will, check the first condition. If R is odd, we retry. We choose another A, which will give us another number R, another, if you will, smallest possible M, which is another R. And if R is even, we continue. We check another condition. If n divides this particular number, we retry because we won't learn anything about P and Q, because P and Q will be confined, will be limited in the second product member. And if n doesn't divide this particular number, thus with the greatest common divisor tool, we can extract P and Q, which are named in here F1 and F2. And the Shor algorithm will focalize, will concentrate its efforts in finding R. The hardest part of this particular process is finding the number R. And if we find R, we can do the rest of the calculations and break this encrypted safe communication. And Shor's algorithm, Shor's process will take the number n, will take another number a, and compute the number r. And this particular process will be reduced to an order finding process, because first it was a factorization problem, and as we evolve, as we detail our process, we arrive to the fact that this particular, if you will, this particular number with a lot of combinations, a lot of numbers m, we notice that every time we have a certain pattern, periodic pattern that appears. And if we want to, and if we, are successful in finding the period of this pattern, which is if you will, which is the same as saying we want to find r, the smallest integer that satisfies this condition. If you find the period or the order of our problem, we successfully have executed Shor's process. So the problem of factorization was reduced to a problem of quantum order finding. And what better tool can we use to find periodic patterns and find periodic information than quantum Fourier transform, and especially the quantum phase estimation. Fourier transform, as we said before, in general, if you will deal with periodic patterns, and the quantum Fourier transform deals with periodic patterns in quantum superpositions and quantum systems information, the information contained in quantum systems in general. So let's take a before we take a look at the Shor's algorithm. Does anyone have a question about this particular step? About this particular step? Okay, perfect. We can move on. In general, the format or the structure of the Shor's algorithm will be represented by two separate quantum registers. Quantum registers contain qubits and quantum information. And in here, we will be having two quantum registers. The first quantum register is the source register, and the second quantum register is called the target register. If you will, you can see this particular setup similar to the setup of the quantum oracle that we talked about in previous sessions. But in here, that is another setup, another, if you will, quantum unitary or quantum transformation that takes two distinct quantum registers and returns a certain fuel output. So we have two registers. The first register will undergo the Hadamard operators. Hadamard operators, as we saw in previous sessions, creates equal superposition. So it returns to us, if you will, a certain superposition that contains equally superposition quantum basis states. And afterwards, we will be having a certain unitary that will be performing modular exponentiation. And we are going to see what this particular part does. And then on the first register, we apply the inverse quantum Fourier transform. So this is just the inverse, the quantum for the dagger applied to the quantum Fourier transform unitary. So it will be the inverse matrix of the quantum Fourier transform operator that we talked about in previous sessions. Quantum Fourier transform, as we talked about, deals with periodicity, extracts periodic informations, and the inverse of the quantum Fourier transform returns us to pre-extracted information state, as we are going to see right now. Let's understand first this particular unitary and the function of this unitary. What does? Okay, I thought I understood the question. Okay, let's dive deep into what this particular unitary does first. So this unitary will act on two quantum registers. Thus, this particular representation, because we're used to seeing operators acting on a certain kit or a certain quantum state, but here we are going to use two quantum registers. Kit of X will be the source quantum register, and kit of Y will be the target quantum register. And this operator takes these two quantum registers as inputs and returns this particular output. This particular output is defined by the first register not changed at all. Kit of X remains kit of X, and kit of Y becomes a to the power of X times Y mod N. What did this particular function, or what this particular unitary do? This unitary operator took the value, if you will, X and Y, and returned to us a certain number A, which is characteristic or inherently associated to the unitary U in here, right here. And A will be, if you will be up to the power of X, the first bit string contained in the first quantum register, multiplied by Y times Y, the second bit string contained in the second register, mod and modular N, and our usual number, usual big number, which is the result of the product between two numbers. And we can notice something in here. If ket of y, sorry, is equal to ket of 1, thus u applied to ket of x, ket 1, will be ket of x, the first quantum register will not be changed, as we talked about. And the second quantum register will be a to the power of x times y will disappear in here because ket of y is equal to ket of 1, modular and evidently. Thus, the second qubit register will contain, like it's represented here, ket 1, not ket 0. For us to, if you will, get in the second quantum register this particular representation. And really, what we are trying to do in here, the first register, the first quantum register, as we talked about, will contain the superpositions, the equal superposition, as we talked about before, and for each and every particular member of the superposition, we will be applying the unitary operator between the ket of x, which is the quantum base state in the first superposition, the first quantum register, sorry, and ket of y will be containing a to the power of x modular n, which is the same expression that we want to find the order of in here. So x in here, which plays the role of the number m, we want to find the order r by detailing each and every possible quantum base state in the quantum superposition contained in the first quantum register. And in the first quantum register, with all these possible possibilities, as we talked about before, one of them will give us our desired number r, which is the smallest possible m. Is the problem that our Shor's algorithm seeks to solve. And the application of the unitary will result in a new superposition, and in this new superposition, there will be a certain periodicity. The quantum base states will repeat themselves. And this periodicity, the order of this periodicity will be extracted, will be deduced by the help of the quantum Fourier transform, the inverse quantum Fourier transform. Quantum Fourier transform, the inverse of quantum Fourier transform, sorry, will take this particular superposition that has a certain order in it and give us the corresponding order, which is the number r. So this is the idea of Shor's algorithm. Shor's algorithm creates a certain superposition of quantum states which correspond to the possible outcomes, inputs of the function, the modular function in here. The quantum superposition contains all the possible inputs of our modular function, and with the help of the unitary u that we talked about before, we will get this particular outcome. This particular outcome, ket of 1, ket of 7, ket of 4, ket of 13, ket of 1, ket of 7, ket of 4, ket of 13, and so on and so forth. It will give us a new superposition, a new, if you will, superposition that contains a certain order, that contains a certain periodic pattern that repeats itself. And with the help of the inverse of the quantum Fourier transform, we will be extracting this particular order, which is the number r. This is the idea, and this is the reasoning between the Grover search algorithm. So let's move on to the next part, how to construct the unitary u. We understood, okay, the unitary u will give us the second register containing the function, the modular function that we talked about before, that will contain the number x, and we want to find the minimum or the least number m that satisfies the condition mentioned above. But how do we construct this particular operator u? Okay, let's take our number x, our number, which is, if you will, one of the numbers or one of the members of the superposition contained in the first quantum register. Our number x is described in the base 10, or in a normal number, 7, 8, 5, 13, so on and so forth. we convert it to binary representation. And this binary representation will contain binary numbers, xn minus 1, xn minus 2, and so on and so forth until x1, x0. Xn minus 1 will be the most important bit, and x0 will be the least important bit. So x, by definition, by the binary conversion definition, x will be equal to xn minus 1 times 2 to the power of n minus 1 plus xn minus 2 times 2 to the power of n minus 2, and so on and so forth until reaching x1 times 2 plus x0. This is the basic definition of conversion between a base 10 number to the binary representation. So if you want to represent this number contained in the second register after the application of the unitary u, it will be a times x, evidently. It will be equal to a times this particular, if you will, base 10 representation. It will be x n dice n minus 1, a to the power of x n dice n minus 1 times 2 to the power of n minus 1, and so on and so forth until x1 times 2 plus x0. And there is a certain plus in here. There is a certain summation. So there are certain plus signs inside of the parentheses that constitutes a power. So if you separate each and every member of this summation, they will be we will be having a result that is constructed by a product of certain, if you will, numbers. So this particular summation inside of the parentheses that are contained in the power will be equal to a times x n minus 1 times a to the power of x n minus 1 times 2 to the power of n minus 1, and inside parentheses times a to the power of x n minus 2 multiplied by 2 to the power of n minus 2 multiplied by so on and so forth until reaching a to the power of x1 times 2 multiplied by a to the power of x0. So in here, from this particular line to this particular line, this summation was transformed into a certain product. And let's see what's happening in here. Each and every member of these products contains a certain binary number, x of I in general, times 2 to the power of the corresponding indice of the binary number. So the creation of a times x really amounts to the creation of this particular product. So if we take this particular number, we create this particular number, and then we create the next number and multiply the two together, and then we create the third number and multiply the two parts together, and so on and so forth, we can reach our number a to the power of x. So this particular representation or this particular creation of the number a to the power of x, you can think of it like having n different steps. In here, it's complicated to create the number a to the power of x because we want to, if you will, include it, or we want to contain it or focalize it inside of a quantum register. And if you want to do this particular number, reach this particular number from the initial quantum register combination or configuration, we can think of it as having n different steps. In the first step, we inject this particular number, and then we multiply it by the second number that we are going to inject, and so on and so forth. Each step, we inject a new number, and we multiply it by the existing product. So let's define a certain small unitary, u of a new unitary, a new quantum unitary that represents a certain quantum gate, quantum transformation that takes a certain quantum state ket of y and returns a multiplied by y mod n. This unitary that has a certain parameter a will take the bit string inside of the quantum state ket of y and multiply it by this number a. So it will be ket of a y mod n. This is the smaller unitary that corresponds to each and every different step that we talked about before. So if you will multiply our quantum state ket of y with the unitary u of a 2 to the power of g times, we will be having this particular outcome. A to the power of 2 to the power of g y mod n. And this is the idea of the different steps. Let's see in detail the representation of the unitary u. This is the representation of the unitary that if you will corresponds to this particular unitary, that gives us this particular number. Let's, if you will see it step by step. Ket of phi 0, the initial quantum state, the initial step will be equal to ket of 1, as we talked about before, so that this particular outcome will be true. Ket of phi 1, which is the result of applying the unitary u with a certain parameter a to the power of 2 to the power of 0, controlled by the first qubit in the first quantum register. What does this mean? If the first quantum state, or the first, quantum bit, ket x0 contains 0, this operation will not be applied, or not be, if you will, applied. But if this particular qubit is ket 1, this operation will be applied, and the multiplication, the first step that we talked about before, will be applied. This unitary, the first quantum unitary that we are going to use in this unitary, big unitary u, will have this particular action. It will give us ket of phi 1, the new number that is injected in our quantum state, which is a to the power of x0 times 2 to the power of 0 mod n, evidently. And it is controlled by the first qubit of the first quantum register. Ket of phi 2 as well. But here we are going to increment the power of the 2 in here. So it will become u of a to the power of 2 to the power of 1. And it will include the new number in here. Ket of phi 3 in here, for example, it will include a certain new number, sorry, resulting from a to the power of 2 to the power of 2, the unitary corresponding to this particular parameter, and so on and so forth until we reach ket of phi n. Ket of phi n, a quantum state that contains a to the power of x0 times 2 to the power of 0, multiplied by a to the power of x1 times 2 to the power of 1, multiplied by, and so on and so forth, multiplied by a to the power of x n minus 2 to the power, multiplied, sorry, by 2 to the power of n minus 2, multiplied by a to the power of x n minus 1 to the power of 2 to the power of n minus 1, which is exactly the expression, if you will, in here. So it will result into ket of a to the power of x modular n. This particular configuration in here that we talked about right now is the representation, the implementation of the operator u that will result into in the second quantum register containing the quantum state a to the power of x mod n, following the superposition and following the quantum state, or the bit string contained in the quantum state contained in the first quantum register. And this is better seen by the sequence of operators being controlled by the qubits of the first quantum register. So the first step is achieved in here, the first crucial and important step, function that we want to find the minimum of, or the least number m of. Here we did the first step, which is encoding the function, this particular function, and this same function, this particular function, into the second quantum register of our two quantum registers. If we successfully encoded this function in the second quantum register, and then we can apply the inverse of the quantum Fourier transform, because this encoding will result in a periodic, if you will, quantum superposition, and this periodic quantum superposition will be affected by the inverse of the quantum Fourier transform, and this inverse of the quantum Fourier transform will give us the order, the period of this particular periodic pattern, or this particular periodic superposition. And if we get the period, we get our number R, and we finish the two conditions and get our two factors. So this is the first step, the first unitary U that constructs our number X and applies to it the modular, if you will, modular application. And before we move on to a rather interesting part of our workshop, let's see this particular claim. So this particular claim states that lambda of k, which is exponential of 2 times pi times I times k over r, this particular number, this particular exponential, is an eigenvalue of u of a with certain eigenstates k of psi k, which is 1 over square root of r times this particular summation. And this particular number is for normalization. As we know, a certain condition, a certain important condition for valid quantum systems or quantum states is that the normalization of amplitudes of these quantum states, the sum of the amplitudes squared is equal to 1. But our claim for every possible number k, this particular value is an eigenvalue of the matrix U of A with eigenstates this particular value. And just a little reminder: if we have a certain matrix or certain operator U, and we multiply it by a certain vector, this is the general case. If we have a certain matrix A, let's treat the general case, a certain matrix A, and we multiply it by a certain vector in here, and we get a certain number, lambda, and the same vector repeats itself, we say that this vector is an eigenstate or an eigenvector, and this particular number is an eigenvalue. And the same thing repeats itself for quantum operators. If you have a certain quantum unitary operator U multiplied by a certain quantum state psi, and it gives us another quantum state, evidently, but with a certain factor lambda, get y, we say that lambda is an eigenvalue of U and psi is an eigenstate of U. And our claim that we want to state in here that for every possible value of k, lambda of k, this particular number, is an eigenvalue of U of A with eigenstates this particular number. And we can dive into the proof of this particular statement. U of A multiplied by the vector psi of A will give us this particular representation. In here, I just replaced k of psi k with its representation. But an important property of quantum systems and quantum theory of information in general is that quantum systems and quantum formalization of information is linear. Thus, U of A can be injected inside of the summation in here. So it will be equal to 1 over square root of R, summation of G's from 0 to R minus 1 exponential. And U of A will be injected in each and every quantum basis state inside of this particular summation. And we know that if we apply U of A to any quantum base state or quantum state in general, it will multiply the containment or the inside of this particular ket, the bit string contained in the inside of this particular ket. It will be multiplied by A, which is the parameter of U of A in here. So from being A to the power of G, it will become A to the power of G minus 1. And it will give us this particular quantum state, quantum superposition, and this quantum superposition is, if you will, indiced by this particular summation with the indice J, if we change j from j to in here we just if you will replace j by j plus 1, we just did a certain shift with the incrementer or the counter j in here. So from j it becomes j minus 1, so it becomes in here you can see it as j prime, with j prime being if you will j plus 1. So j will become j prime minus 1, and j being from 0 to r minus 1 will become j prime from 1 to r, because we change j by j prime, we change the counter of the summation in here. And this particular representation can be expressed by this particular representation as well, because if j prime is equal to r, if j is equal to if j prime is equal to 1, we can shift it to j from 0 to r minus 1, and this particular shift will, if you will, output a certain factor in here, exponential minus 2 times pi times I times k times j. So we just extracted one particular if you will, member of our summation in here, and it will result in a certain if you will, summation multiplied by a certain exponential in here. And this summation is if you will, is the same as ket of psi k, and this particular number is equal to lambda of k. So really, we just extracted this number, this exponential, from the summation inside of the quantum superposition, and showcased that it is evidently a eigenvalue of our, if you will, matrix u of a, or operator u of a. So this is a simple claim that will be important for the details to come. So in here, we deduced that for every single matrix, every single operator u of a, u of a certain parameter a, this particular, if you will, operator, or this particular quantum operator, has multiple eigenvalues, lambda of k, which are equal to exponential 2 times pi times I times k over r. So for every possible, or for every single, if you will, value of a in here and in here and here, etc., etc., every single operator that is controlled by the first quantum register has, if you will, a certain set of quantum eigenvalues, lambda of k, for each and every quantum operator. And these operators, eigenvalues and eigenstates will be crucial to understanding the details to come. So, if you didn't realize already, the quantum phase estimation algorithm that we treated in the last session has a similar structure to our proposed Shor algorithm. Let's recall the quantum phase estimation configuration. The quantum phase estimation takes as well two quantum registers, quantum states in general. First quantum register will undergo the Hadamard operations. The first operator, the first qubit, the second qubit, up until the last qubit, will undergo the Hadamard operator. This step, as we talked about in the previous session, will create an equal superposition. This equal superposition will lay out in front of us in the quantum superposition all possible quantum basis states for our first quantum register. And with the help of the controlled operations of u to the power of u to the power of 2 to the power of 0, u to the power of 2 to the power of 1, etc., etc., until u to the power of 2 to the power of t, and with the help of the quantum Fourier transform, the inverse of the quantum Fourier transform, of quantum Fourier transform dagger, we can measure an n-bit approximation of ket theta, with ket theta, or theta in general, being the if you will, the phase, if you will, or the number that is contained in exponential 2 times pi times I times theta. And this particular number is an eigenvalue of the operator u. So for the quantum phase estimation, we have a certain operator u, which has one single eigenvalue, exponential 2 to the 2 multiplied by pi, multiplied by pi, multiplied by I, multiplied by theta. And this particular theta, we want to find its exact value, or at least an approximation of this value. So what do we do? Really, we just take the first quantum register, put it in a certain quantum superposition, an equal quantum superposition, and we apply these, if you will, consecutive controlled operations that will create a certain superposition that is periodic also, with a certain period that will be extracted by the inverse of the quantum Fourier transform, and we will be getting a certain approximation of theta by measuring consecutively, and a lot of times the first quantum register, and getting the n-bit approximation of that theta. So the QPE, the quantum phase estimation circuit, takes a certain unitary operator U, and by applying it sequentially with some powers, sequentially with putting it up to the power of 2 to the power of some numbers in a consecutive way, it will measure the phase of that value, of that eigenvalue that is corresponding to our operator U. And the Shor algorithm does the exact same way. Does the exact same thing, because it wants to reach the exact same, if you will, outcome. The quantum phase estimation, as we said before, extracts these particular numbers contained in the exponential, and Shor's algorithm seeks also to extract these particular, if you will, numbers contained in the exponential, because these numbers, these real numbers, contain R in them. So in the case of the quantum phase estimation, we have, as we said before, the eigenvalues of our operator U in the form of exponential 2 times pi times I times theta. And with the quantum phase estimation, we extract theta exactly the same. We have in here an operator U of A to the power of 2 to the power of some other number, and each and every if you will, power of this particular operator, this operator still has not one but many eigenvalues in this particular form, exponential 2 to the times of pi times I times k over r, with k changing as the eigenvalue changes. So in here, we will be extracting all possible k over r's. In the quantum phase estimation, we extract just one number, ket of theta. Afterwards, in the consecutive measurements, we notice that there is a certain peak that corresponds to ket theta. In here, in the quantum Shor algorithm, we will be noticing the exact same thing. We will be extracting the orders of the values, the real values contained in the exponential of the eigenvalues of U of A. But we won't have just one eigenvalue, but many eigenvalues. Thus, we will be observing a lot of peaks, if you will, or a lot of, if you will, high measurement outcomes compared to the other outcomes that will correspond to the values of k over r. This is the genius of the Shor algorithm. It implies and it uses the quantum phase estimation protocol to, if you will, create this particular order detection process, but for a lot of eigenvalues. And each and every eigenvalue of these fuel measurements will be k over r. So it will be 1 over r, 2 to the 2 over r, etc., etc. For example, we can notice in here a certain probability versus a result chart in here, where 0 will have a certain peak, evidently, because it is also a valid, if you k over r outcome. 1, 2, 3, 4, 5, 6, etc., etc. These outcomes will be measuring not k over r. This is just a remark, but 2 to the power of n multiplied by k over r, so that our outcomes move from a certain binary approximation to integer normal approximation. So for 0, we notice a certain high measurement probability. For 4, we notice a certain high measurement probability. For 8 as well, we can conclude from these particular observations that we will be having a certain peak in 4, in 8, in afterwards 12, in 12 also, but it is not shown in this chart. So now we'll be proceeding to find out the number R value. If n equals 3, if our number n equals 3, we have a peak at 4, thus 4, which is the peak, will be equal to the first, if you will, real number contained in the first eigenvalue, which will be equal to 2 to the power of n multiplied by 1 over r. The first, if you will, value noticed, or the first, if you will, eigenvalue noticed. So 4 will be equal to 2 to the power of n multiplied by 1, k is equal to 1 in here, over r. And n in here, in this case, is equal to 3, thus r is equal to 2. If you take another example, another case, n is equal to 5, r will be different. R will be equal to 8. And there is another systematic way to do this particular task called the continuing fraction algorithm, but I didn't detail it in this particular slide because I thought the session would be too long if I did. But it is a certain way with continuous fractions, with continuous, if you will, approximations, and a certain, if you will, assumption, a certain mathematical assumption, with continuous fractions, we can conclude, and we can, if you will, with the help of the measurement values that we notice in here that have a lot of measurement probability, we can notice the exact value of R, or at least the approximation of the value R. So this is exactly the, if you will, incredible genius of the algorithm of Shor. Let us, if you will, do a overall recap of the genius of the algorithm of Shor. The Shor algorithm wants to solve the particular task that we talked about before of finding the, if you will, order R of our modular function. And it starts with the first register being also, of course, in the state get 0 for each and every qubit, because it is the initial state of each and every quantum circuit, evidently. It will undergo a certain Hadamard operator for each and every qubit. It will give us a certain quantum equal superposition. And this quantum equal superposition will undergo the function, the modular function that we talked about before. This, each and every part of this quantum superposition will undergo the modular function that we detailed in the beginning of this session. Yeah, this one. So it will transform the second register to this particular function, depending on the value contained in the first register, evidently. And this particular superposition, as we talked about in here, after this particular operator, will result in an equal superposition, in a periodic superposition with a certain period that we want to extract. And this is the job of the quantum Fourier transform inverse that will give us the, if you will, quantum state that contains the period that we talked about. And after measurement, we will be noticing peaks corresponding to 1 over r, 2 to the power 2 over r, 3 over r, etc., etc. This is exactly the functioning of the QPU that extracts the field order of a certain value contained in the eigenvalue of the operator U. But here we will be having a lot of eigenvalues, that we will be having a lot of k over r's, and just by looking at the first peak after the 0, of course, we can conclude our value of r equal to what? And this part will be injected in the overall approach, where the few values of a and n will give us a certain r given by the Shor's algorithm, and we will be processing and will be if you will moving on to the next steps. And this is exactly what we did in here, but with a quantum way. So all these possible, if you will, all these possible inputs for the modular function in here correspond to the equal superposition given by the Hadamard operators. The Hadamard operators will give us get 000, get 001, get 0010, etc., etc. And each and every, if you will, number of these quantum-based states contained in the superposition will be exactly like the inputs that we did inject in the modular function in here. So up until this point, it's like we did the Hadamard operator in the quantum circuit, but here we are dealing with, if you will, handwritten, hand checking of our modular outputs. And the modular function, these outputs will be given in the quantum context with the unitary operator. The unitary operator will take this equal superposition and transform it to a periodic superposition. The periodic superposition that we observed in here, the periodic pattern in here, will be translated in the quantum if you will, case, or the quantum context afterwards, in a periodic superposition. And this periodic superposition have a certain period R that, if you will, describes the repeating of this particular periodic pattern. And this particular R will be extracted with the help of the quantum Fourier transform inverse. And this quantum Fourier transform inverse will give us a certain quantum state in here that, with consecutive measurements, as we do all of the time, with consecutive measurements, not one measurement, because one measurement gives us a certain random outcome, but with consecutive measurements, we build up probabilities, and with these probabilities, we can deduce the previous quantum state before measurements. This particular quantum state will give us the exact order, exact R, that will help us afterwards in the next few steps. And the representation of U will be, if you will, like the representation of the modular part of the quantum phase estimation, where each and every operator controlled by a certain qubit in the first register will, if you will, inject a certain number in the overall multiplication. So U of a to the power of 2 to the power of 0 will inject this particular part. U to the power of a to the power of 2 to the power of 1 will give us this particular part, and so on and so forth, until the first controlled operator, where we will be deducing in the second register the a to the power of x mod n quantum state that we will be using in the next few parts of our algorithm. Okay, just a side note here before notebook. Shor's algorithm complexity will be equal to O to the power of 2O of log of n to the power of 3. It is a polynomial complexity compared to the if you will, classical best algorithm, which is the number field CF, which is equal to exponential of big O of logarithms inside of the exponential of the detailed exponential, which is a supernomial time, a very, very expensive algorithm, or a very, very expensive process to be run in a classical computer. That makes it classically, it's virtually impossible to factor our number, which makes the RSA encryption scheme safe up until this point. If we apply the Shor's algorithm on a quantum hardware or QPU in general, it will give us an exponential speedup, and it will break the RSA encryption scheme, and it will break any other encryption scheme, because they are all founded, or they are all, if you will, following the principle is that big numbers are really hard to factorize. And this is exactly why the quantum threat, if you will, algorithms and quantum computing threatens classical encryption. So let's do a little bit of more details of Shor's algorithm. Many quantum algorithms are, if you will, constrained in some scientific simulation, quantum chemistry, chemical simulations, or optimization, quantum optimization, or quantum AI. But for Shor's algorithm, it is a very, very important algorithm because it targets the computational bottleneck or the computational possible aspect of a certain problem, integer factorization. And this particular, if you will, assumption is the foundation of virtually a lot of cryptographic and security, if you will, protocols. But with Shor algorithm and with quantum computing, we are able not only to improve performance of certain algorithms or certain problems, problem solving, if you will, algorithms, but quantum computing in the field of cryptography and cybersecurity is threatening to redefine entirely a certain entire field, which is cryptography in general. Because, as we said before, with the RSA encryption scheme, the Diffie-Hellman scheme, the elliptic curve cryptography scheme, all are based on the fact that if you will, factorization or if you will, big numbers factorizations is possible or is very, very computationally expensive and demanding. But here, Shor's algorithm intervenes to disrupt all the foundations that classical cryptography is based upon. And Shor's algorithm actually is the main driver and the main, if you will, catalyst of a totally new domain, which is post-quantum cryptography and quantum cryptography in general. The domain of post-quantum cryptography seeks to develop algorithms and develop systems that are safe of classical and quantum decryption, are safe of, if you will, quantum threats to all the basics of classical cryptography. And it is quite fascinating how far such an technology and such an, if you will, quantum process has come. Because right here, we are not talking about just improving the functioning of a certain domain. No, we're talking about disrupting, and if you're redefining entirely what a certain domain does. Because if you will follow with classical contemporary encoding schemes, classical encoding schemes, we will be put in a very hard position once quantum hardware matures and once quantum error is totally annihilated. So it is a emerging domain similar to some domains, quantum AI or quantum optimization, quantum simulation. These are domains that seek not only to, if you will, optimize some aspects of their respective applications. No, they seek to totally shift the technological landscape in the worldwide technological landscape. The same thing with quantum AI. Quantum AI with the properties of superposition, of entanglement, of parallel computing, etc., seeks not only to, if you will, improve machine learning, improve AI, but redefine the entire game of of AI optimization, AI classification, and other, if you will, domains fundamentally, which is the case of a lot of other quantum fields in general. But here, we need to focus on this particular domain, which is gaining a lot of traction and it's gaining a lot of, if you will, reach in the international scale. And a lot of startups and a lot of companies are actively looking for engineers that are, if you will, that are specializing in post-quantum cryptography. So I urge you, if you are interested by this particular session, I urge you to dive deeper into this particular field, and if you like it, you can follow it up as a future career. Okay, without further ado, let's move on to the Shor algorithm notebook, and let's follow step by step with the Shor algorithm implementation. For example, let's start with the example of factoring 15. This is a simple example, but it will be beneficial in our learning. As we talked about before, factoring a certain number, we will need first to define a certain number, a, in the interval between 2 and n minus 1, and here being 15. Let's choose a as 7. We want to find the period r of the function f of b. Here we mapped 7 to the power of b mod 15, and we can describe it as, sorry, as a function f of b, which is a to the power of b mod n. Let's take a look at this particular function. Let's use the construct mapping function that we defined in the beginning of our notebook, and it will give us this particular table. It will take n and a as inputs, and it will give us this particular table as output. It will give us the output of 7 to the power of b mod 15. From this particular table, as we saw before, we can see which is what is the number r. It will be equal to 4 in here because it is the period, the order of this particular periodic pattern. But here we want to define it and extract it with quantum circuits implementations. So we can define a quantum register, two quantum registers, actually, sorry, a classical register, a quantum circuit, and we can apply Hadamard's on all the source qubits or the source register qubits. And then we apply this particular unitary that will implement unitary U or the consecutive controlled applications of the U to the power of 2 to the power of u to the power of a to the power of 2 to the power of u of a to the power of 2 to the power of consecutive integers. I'm very sorry. Okay, let's add. We add also this particular unitary as we talked about before, and we apply the inverse quantum Fourier transform. We import it from the Qiskit library. We do a certain barrier to improve visual representation, and we do measurements on the first quantum register and store it in the classical register that we talked about, which was the backend of Qiskit's AR simulator backend, and we do a lot of measurements. And what do we notice? Sorry, what do we notice in here? Sorry, this is a, if you will, perfect simulator without noise, without all the quantum hardware problems. And we notice in here that we measure 0, 4, 8, 12, etc., with a higher probability than the other outcomes. What do we conclude from here? We conclude from here that 2 to the power of n to the power of n multiplied by k over r will be given by these particular values, and then we can deduce our r. Our r will be deduced as 4, as we talked about, and these particular calculations in here. So here our n is another value, but we can conclude our r, and we move on to verifying the two next conditions. R here is even, we move on, and the greatest common denominator between the number n and the other number is not n. So these two numbers, if you this particular number is not, if you a multiply of n. Thus, we move on to the second, if you will, step, or the third step, sorry, which is extracting the factors of n. F1 will be the greatest common denominator between a to the power of r over 2 plus 1 and big N, and F2 will be the second, if you will, factor, which will be also n over F1 directly. And we deduce that the factors of n are 5 and 3. We here did the if you will, entire process that we talked about before, and we concluded the values of n. The values of the factors of n. Let's take another example. Factoring 21. N will be equal to 21, and a will be picking it as 17. And then n and a are co-prime, so it will be correct. So we will be mapping the output of the function f of b as we talked about before. This is the particular mapping. We can notice that r is equal to 6 in here, but we can also apply this particular circuit. We can deduce from these particular measurements the value of r, and we can also, if you will, do the f1 and f2 multiplies. But in here, the two factors of n are deduced to be 21 and 1. This is not an important, if you will, outcome that we want to reach. We want to reach 7 and 3. But here we reached 21 and 1 from the factorization process. Thus, we deduce what's wrong in here. We deduce that the choice of A is not convenient. We try again with another value of A, which is equal to 11, co-prime to 21. We do the exact same process. We do the mapping, and we do the quantum circuit. We do the consecutive measurements that build up probabilities. We can, if you will, deduce our value R, and we deduce that the two factors, after applying the greatest common denominator on the second step, we deduce that the two factors of n are 3 and 7. This is an appropriate A for our special case of n equal 21. So this is just a challenge problem that you might use to, if you will, practice. And just a little thing in here, I didn't detail this in the beginning of our session, but this particular function, the quasi-modular exponentiation, that implements the, if you will, the controlled operators part before the inverse quantum Fourier transform, the modular sum part, is not exactly, if you will, in this notebook is not exactly detailed how did we implement these particular if you will, quantum operators. In this particular operator, in the if you will, sake of visualizing and better improving the visualization of our quantum circuit, I took just the output of these tables as outputs of this particular operator, which is the visual representation of our operator. And just, if you will, copied the output of the modular function from each and every input in this particular function first. So there is no definition of operators or something like that, but depending on the table that we, if you will, detailed before the quantum circuit, I just affected every input to its output, because the process of building these particular quantum operators, these particular quantum controlled operators, is very, very hard. It requires a lot of complex calculations, a lot of complex quantum circuit calculations, but I included them, I included them in another quantum circuit, another, if you will, notebook in here. It's very, very long, but they contain all the needed parts that, if you will, that are used to construct these quantum operators. The quantum adders, the quantum modular calculators, the quantum exponential calculators, a lot of functions and a lot of mathematical, if you will, rigor in here. But the important thing is that this is exactly the true application of the modular part in here, or the controlled part of our quantum algorithm, but in further detail with the modular calculations and the modular arithmetics, or quantum modular arithmetics. And for example, I plugged in the example of the last cell. I plugged in the example of A equal 11 and N equal 21, and it gave me the outcome of the factorization, 7 multiplied by 3 after 53 minutes. So this particular cell, after the definition of all the functions in the beginning of this particular notebook, this cell, which executes the overall algorithm, lasted for 53 minutes for such a simple example. Imagine that if you want to factor a big problem, it will take a lot of time. But in the context of quantum computers and quantum hardware, it will be in a reasonable number of hours, corresponding to the corresponding to the complexity of the Shor algorithm being big O log n to the power of 3. So this is just a remark. This particular function simplified things. I just, if you will, took the output of the table in here and affected it to the input, which is really the action of the modular part or the controlled part of our algorithm. And I just applied the quantum Fourier transform, inverse quantum Fourier transform as given or as provided by the Qiskit library. So this is the end of our session. I hope it was rather a heavy session with calculations and arithmetic calculations, but I hope it was clear. Does anyone have a question about the notebooks, about the slides of our representation? Okay, perfect. I believe no one has a question, but if you ever have a question about this session or about any session that we tackled together, I'm more than free to answer all of your questions in the WhatsApp group or in LinkedIn or in any other way of communication. Okay, thank you so much, and I hope it was a beneficial and an important and beneficial session for such an important field, because post quantum cryptography, just a side note here, is one of the leading fields in quantum science and quantum science and technology in general right now. And I urge you, if you liked this particular session, I urge you to learn more about it and dive deeper into this particular field, because it is very high in demand, and frankly it's very interesting. Because from these particular notebooks, in the complete Shor notebook, it might seem like a little bit intimidating, but believe me, once you dive into it step by step, it will be a lot fun. Because in my community in Tunisia, we have a member that, and she is, if you will, and she is very passionate about quantum cryptography and quantum post quantum cryptography, and she is a lot of she tried to follow step by step the research papers and the few workshops existing in the internet. So if any one of you wants to dive deep into this particular field and wants to have some resources, I can also give you some resources to follow up and to advance in this particular field. Thank you for your attention, and good night.